So yeah, SI is your time to learn, to study, to ask as many questions as you want, and to really like accomplish a moment of, you're kind of like, you're like, yeah, that looks like that's something that I can do. And then you start doing it and you're like, wait, I actually don't know how to code that at all. So that type of moment is like best to have at SI, because you have like your classmates here, you have me here, so we can help you. You never want to be like working on something alone and you're like, wait, I actually never understood what that thing was that Dr. Erickson was talking about in lecture. So definitely ask away anything that you want. Today, we're going to talk about binary tree data structures, and we are also going to talk about recursion. But depending on where you guys are at with recursion, like how comfortable you are with it, I am prepared, like either to talk about the trees a lot, or I'm prepared to talk about recursion a lot. So I kind of need you guys to let me know which way you want this to go. Recursion is going to be a huge part of trees. We'll talk about recursion. So for you to do well with binary trees, and it's like a data structure that get asked in it, like it comes up in interviews all the time, and it's like in the most annoying ways that you could ever assume, right? Like they say like, here's a binary tree, make sure you flip it, or maybe make sure that you reverse it, or like find what node is missing. It's just very deep philosophical questions about binary trees. So in order to do well with this data structure, you need to have a strong grasp of pointers in C++. Even if you're gonna like interview using Java or Python, still it's really good to, it's really like the fundamental knowledge for this data structure is knowing pointers, okay? So if you've made it somehow this far in the semester and you're still kind of like, I don't know how pointers work, then you have to make sure that you learn them, because you already seen them in linked lists a lot. And another thing you need to know to do well with binary trees is that you need to have like a knowledge of common data structure algorithms, which is like, hey, you have a data structure, what do you need to equip it with, which is insert, delete, append, prepend, all those type of things, right? You need to like kind of like have a visual map of like, how do I implement this algorithm in regards to this data structure. And of course, you need to know templates, which I think you guys should be comfortable with, because you've done like a couple of homework assignments, and every single code that Dr. Erickson has done has been using templates. So if you're, for some reason, you're kind of like, I still don't understand templates, which I think no one here is like that, then you should look into them and learn them as soon as possible. So let's bring it back to recursion. Recursion is literally the exact same thing as the Russian doll situation. It's another way of looping. Whereas in a loop, you would be always in, like it would be the same thing. You have the same, let's say you have only one doll, and that would be the loop. And it always performs the same task. It's one thing. It's one entity that does that thing over and over again. But with recursion, you have this Russian doll situation, which like this doll passes to this one, this one, this one, this one, this one, all the way down. And then sometimes there's a way to wrap it back up and bring it back to this one. I'm trying to talk to you conceptually before I step into like code and stuff. Let me share the link for today's Replit, because I am going to start coding now. So I usually use Replit, which is a very convenient website for you to just have a link of, all the code that I'm doing today. You can like refer back to it after the session. You just gotta refresh the page and just go use the same link, okay? So how would you explain recursion at the moment, right now? How do you understand it right now?
It's just calling one function again and again until we hit the base case. That's right.
Okay. Yeah, I like those words. You're calling the same function again and again, and we have this thing called base case. That's great. Yeah. So call the function from inside of it. Is recursion similar concept to a while loop? Okay, so I like the one that says call the function from inside of it, but then the answer to the question, is recursion a similar concept to a while loop, right? So a loop, that's why I'm saying like a loop is, you would have only one of these dolls. That's a loop. It's only one doll and it like performs some task. Recursion, you get to have multiple instances of the same thing. The way that it works is like this. So right now I have a function called oh my god, that's such a name. Like, let me just call it like print something. This is called the print something method, right? So the way that you would use this is you would come into your main and you would just call print something like that. You could write a while loop, while, and you call print something and you call it like with like number 4. The loop is one entity, one thing, object. I don't want to say the word object, but it's like one doll that continuously calls this one function. Okay. But in the realm of you always being able to put your code away in some sort of a function, what is stopping you from calling a function from its own body like this? And the answer is like nothing is stopping you from doing that, right? It's like, where can you call a function? The answer is anywhere, whether it be within the function itself or from outside of another function, which here they would be the main function. You could call a function wherever you want, right? So for a while loop, you see that this would only create one instance of this task being done. I'm calling it only one time and I'm giving it this number 4, and then it's going to print out high, okay? But now if you call print something just by line 10, what you're doing is that every single time you are creating another instance of this process in your memory. And that's like exactly, you call it one time, you call it another time, you call it another time, and another time, and it just goes on until the whenever you want to stop it. So think of functions now as a process, as something, as a command that your CPU takes in. And it's very convenient to use the Russian doll example because they all do look alike, because it is the same guy. It's the same function that you keep calling, but with various values. Obviously, if you this while loop that I wrote is while true, this never breaks out because I never said like break, or I never put a good condition in here, right? So right now with line 10, the same thing would happen. You're in a continuously, you're just like, this function gets called once again, that's another doll. This function gets called once again, that's another doll, right? So that's why Amandip was saying you need something called a base case. And a base case is when you got to this little one here, stop, throw it back to the other, to the previous ones. So you want to think of it as like, you know, like a fan, like it like goes like, it like opens up, but then after it's done, it just goes like again, like it just like a stack, it opens up and then it closes back itself up. So like this would be gotten rid of, all of these would be gotten rid of, and then you would only have this original instance. And it's the same thing that I'm talking about, that like let's say I commented this line out, okay, and this is just a print function for saying hi, okay. When you use line 10, line 11, when you call this function, everything about this function has its own scope, right? So like right here, if I say like I is equal to 9, something like this I is something that's very local to this function itself. Once it does, your program, the flow goes like this. It does line 11, it prints something out. It does line 12, jumps to this line of code here. Then it does number 4, then it does number 5, but then you get to the end of this function. So everything that's within the scope of this function, it just disappears off of your memory, right? You no longer have this local variable called I until the next time you call it, right? So in the same way, when you have a function that continuously calls itself, after it touches the base case, which is that like condition of like stop here, stop creating new instances of yourself here, then this little one and this little one, this little one, all of their scopes close out, all of their local variables, it all closes out, and then you have a single function, and then even then it will hit the closing braces and it will like all close out on its own. A little bit too theoretical. Let me get you some code, but let me know if you have any questions right now. So usually I have like this one tab that's like one file that's like has all the questions. This is very related to binary search tree, so we're just gonna like maybe forget about these for a second. We're gonna do like recursion. So the question is, what is the exact output of this function when the when it's called with number 5. 5 is just the right number to get like enough exercise with this, but then also get annoyed a little. So again, I like to like start off by like drawing very silly examples, but it always like helps to start off with like drawing out things that may seem a little like insignificant. But with recursion, you want to get very comfortable with drawing as much with anything else in this class, basically. So when I say like think of these things as like one Russian doll, I'm literally talking about that. Like think of it as one process. So I'm gonna choose this shape for no reason. This is a blob. This represents this task, a process called message, okay? You might even think of this as an object, as a whole object, because it is like it becomes an entity. It takes up its own space in the memory, right? So first we call it with number 5, okay? So here is number 5. It comes from wherever this, let's say it's the main function. It comes to line 4. Local variable is 5. So we're here, we're going to draw a 5 here. So it has a check mark. It says, is 5 greater than 0? Yes, it is. So it will print something out. Like here is our C out is here. Like this is our console. Like here's a scribble about like what it says. Then it calls itself again. So the way you draw that is, here's another instance of it. Here's another doll. But this time it goes like 4 because 5 minus 1 is 4. So this one is called with the instance 4. Oh boy, that's a 4. Yeah. Then on your console, it prints something out once again. So then it comes to line 7 once again, right? Here we go. Here's a blob. But what is the value of times this time? It's a 3. Now, I'm very careful about not deleting these yet because this is a stack situation. It's using your heap memory right now. There's instances that are active. This is waiting on line 7, the same as this is waiting on line 7. And this is literally still on line 5 because it's got to ask, is 3 greater than 0? Yes, it is. So let me print something out. Then it goes to line 7. And line 7, it hasn't computed itself yet. It hasn't like finished yet. So it's gonna create another instance. Now we're back up on line 5, but this time the value of times is 2. And for this instance, all of these guys are pending on number 7. This one is on line 6, blah, 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 blah. Line 7 one more time. Here's another blob. I mean, I'm kind of running out of space here. But 1, print something out. Great. So far we've got 1, 2, 3, 4, 5. And 1 is on line 7. So it goes back up here and it calls a number with number 0. So now this is the instance, right? So now it asks, is 0 greater than 0? No, it is not. So this is an if block. It's going to come to this closing braces. Nothing has happened to the console. You have 5 times 1, 2, 3, 4, 5 printouts, but how many instances did you end up making? 6 of them. Like this had to be created so that this function, this line could be evaluated. So now this one closed. It came to the closing braces, right? So we're done here. This is done. It actually gets like removed off of your memory right here. For number 1, where was it pending? What line is this instance of the function waiting on? Number 7, exactly. So number 7, it just finished, right? So now it goes out of the if block, out of the function. This is done too. Just like any regular function, all of its scope and all of its local variables are getting like, you see like it's closing itself out right now. So same thing, all of these are waiting on line 7, so they all just get closed out. We're closing. And then the original one, this one is this doll, this bigger one, this one, this humongous one. It is now all done, right? So even this gets closed out because that just happens with every function. And now the control of the program comes back to wherever this was called. Like let's say it's in the main function. Okay, so let's do another one. So here we go. Write the exact output of this program and all the instances of the function. So this is standard factorial stuff. This is a 4.
I have a quick question about this function.
Yeah.
So we plug in 4,
Mhm.
and then it runs down to the else statement, and it says return 4 times factorial 3. And
Mhm.
so now that thing is stuck on line 21, one blob, and then the 3 runs down. I guess my only concern is when we get to 1, is it just going to return 1 instead of actually giving us the answer of 4 factorial?
I could draw it. My goal is always to draw these anyways because I want to get you guys in the thing. So here's what we have, okay? And here's what n is equal to here. Initially, we come here and n is equal to 4, right? So we got a 4 here. And it does the check. 0, no, this, no. So else, return, okay, I'm waiting, 4 multiplied by this. So this is going to trigger another one of these guys, another instance of these guys being created. Here we go. So now this is calling the value 3. Now we're calling it equal to value 3. This is stuck, right? So 3 is not 0, not 1. So it comes here. So now n, in this instance, it's a 3, right? So 3 multiplied by something. What is that thing? We don't know. It's going to branch out. So now we're calling it with number 2. Now in the scope of this little process, this instance of the function, 2 is a local variable which for n. So now it's gonna say 2 is multiplied by something. Multiplied by what? We don't know. Okay, let's make another instance. Now we made it with 1. So the 1 is the value that n has, right? This guy does not see anything before or after it, right? It's just literally a computer that's working with different instances of the same function. What's going to happen here in this instance?
It just returns 1, right?
Exactly. It's going to just return 1. So you got this instance that's created. It's not a 0, but it is a 1. So let me return 1. It's going to come back here and put the 1 in here. Okay? So now I'm gonna like cross this out because this is like this instance finished. Like it did all of that it had to. It came to the closing braces. So now this one was stuck on line 21, and now it has an answer for this thing in the equation, which is number 1. So now it's gonna do the computation first. The multiplication is gonna happen first. 2 multiplied by 1 is 2. Now it's gonna execute the return. So we're gonna come back here, and this guy is gonna get killed. It's gonna like close itself out. So we're now back at this instance. We're on line 21. It was waiting for this part to be evaluated. It's a 2. So now it can do the multiplication. Do you see that this is a 3-step thing? One is get this value, then multiply, then execute the return operation. So 2 times 3 is 6. We're coming back up. This guy's done. So now we're back on this instance. First step was get what is the factorial of n minus 1? It's a 6. Second step, perform the multiplication. It says return, and now this guy can die off, and now we have a number 24.
So the return in this situation doesn't necessarily mean like break from the function. It just means return that to the previous instance.
So first of all, return is going to be the last step in everything that's happening here. And then second of all, it's not like so you need to think about the memory right now, right? There's a stack thing happening, and every instance here, it's waiting for something before it or something after it. There's nothing here, like when this 2 is stuck on, let me get this value, there is no way that the CPU is gonna like it's gonna be like, oh, discard all of this, all of these instances are gonna die, and I'm just gonna like evacuate everything, right? You need to think about them as very different instances of the same function. It's like the same process, but it's like different. So if this one dies, there's things before it that are waiting for it, you know? So return here, it just means like any other regular function, you know, like before you before you clear out all of the space you took with all of your everything that's within your scope, just throw this value back to whoever was waiting for you. And in this case, it's these instances of the same method. They are different dolls. They even have different sizes, but it's the same doll, you know? So my next question is just do like a lightweight linked listing. So write the algorithm of a function that displays the content of a linked list in reverse order. So what I mean is that you have like a 3, 4, and then a 5, which points to nothing. This, I would want you to print a 5, a 4, and then a 3. And this is a single linked list. Are you guys doing fine? Like, do you have a mental image of what you want to code out? So just to give you an idea of like how terrible this would have been if this was iteration, this is head. If you were to do this using iteration, one of the things that comes to my mind, which is like a very like, might be like the most naive way of doing it or whatnot, but this is like the first sort of like first idea that would pop up in my head, is pretty painful, which is just because you only have one thing, which is called head. So I can like create a pointer, call it traveler, and this guy is going to start from head, and it's going to go from here, here, and then it's going to go here. Once it finds the last node, then it's going to print it out. But it's also, you want to mark that I already printed this out, right? So you might want to like create another pointer that holds the address of this and says I'm done. So then again, you don't have a way of coming back from where you are at 5, right? So you point traveler to head once again. It goes to 3, it goes to 4, and it stops here because it knows that its next is something that it's already been printed. So then you print out 4. Oops, 4. So now done is gonna come and it's gonna point to this guy here to mark that, hey, we've already printed this out, we're good to go. Then you got to start from all over again. Like you print it out once again, you start the loop once again, you point traveler to head, and it's not going to advance again because its next is pointing to wherever done is pointing to, which means like I've already printed this out. So then you're going to print out 3. So you had 1, 2, 3 nodes. You had to loop through this like that many times. Maybe like lines of code wise, it's not like that bad, but it kind of does feel like a bit tedious. It's like I was already at 5 and I clearly walked down 4 and then I walked down 3 as well. Why couldn't I just like somehow remember those numbers? Do you guys have another idea of like how to accomplish this?
I think I was about to do something similar to this, and then I realized that it's probably not the best way.
Okay. So after the semester is over, you guys are gonna have to like go really hard on like lead code type of problems. This is a very easy 2 seconds of thought type of lead code problem, which is essential for interviews. Another way that you would accomplish this is that you would use a stack. And the way that works is that I'm gonna get rid of this done guy. I'm gonna still have traveler, and I'm gonna have a stack like this, and it doesn't matter how you implement the stack, if it's like implemented with an array or a linked list. At this point, you would be using a built-in stack. You wouldn't be developing your own stack data structure. So you point traveler to head. You say I start at 3. Okay, so 3 comes here. And then you point it to the next guy, 4. You dump the 4 into your stack. And then you advance traveler once again until like it goes to the end of the list, and then you again add it to your stack. So this is the top of the stack. It's like the last in is the first out, right? So this is the last one out. And then at this point, all you have to do is you have to just say pop, pop, pop. So you take your array, and until it's empty, you keep popping. And whenever you pop, you print it out as well. So you get a 5, this is removed. You get the 4, this is removed, and then you get the 3. And now your stack is empty, but you have the reverse order, right? The stack is something that you guys already know. It's very easy, like just reverse order type of stuff. So now let's use recursion, which is instead of you creating the stack data structure and dumping things into it, you use the heap memory, which is the stack. And that's what I'm talking about. Like it goes like like that. Like it opens up and then it goes back up. Like it creates instances of itself, but then it also closes itself back out, right? When it closes itself back out, meaning that you do not have to say pop, pop, pop until my stack is empty. You just create new instances of your function. So you need to basically like think of recursion as something that uses heap memory, and you're just like basically creating a stack on the memory. So what I need is like basically like a function that goes like, it's like a void reversed print, something like this. So every single time, what are you going to land on? What are the things in this data structure that you land on? Nodes, exactly. So nodes. So I need to pass nodes in and out of this function. So what should be the parameter of this function that is going to be recursive? Yes, a node pointer. Let's call it like node, something like that. Let's think about like one node here, just one node. This is a node that I'm at. Let's pretend that these other two do not exist. I'm here. What I need to do is I need to print out the value. Okay, so that's easy, right? Let's say cout node.value. That's really all that needs to happen. Like every single time, I just want to see what is the number here. However, when you're thinking about like nodes and stuff like that, what is something when you're messing with memory, what is something that you should always be checking for? Should the dot, yes, thank you, David. It's not a dot operator, goddamn C++, it's an arrow operator. That's very valid, thank you. So every time you need to be checking if node is not equal to null pointer, because that is just a memory safety thing that you always do. Oop. Okay, so if the node is not a null pointer, then I want to print it out, right? However, I don't want to be like, as I land on this thing, because remember, something from the outside is gonna call this reverse point, is gonna call this with the head. Okay, so you're still gonna start with head, which is pointing at it here. You still don't have a way of going back and starting from the back or from the tail, right? We just have a head here. So I still don't want to just be like willy-nilly being like, okay, I landed here, then I landed here, then I landed here, like print, because that would give you the regular order of print. You want it to be reversed. So wouldn't you need to wait until you're all the way down here to print? Any ideas now, or okay, no ideas, that's fine. So what I'm saying is that in the previous ones, you were checking, is it this value? If it is this value, then return. And then if not, then do some computations and then return. With this factorial one specifically, it went all the way down. You had like 5 instances of it open up before you were able to get anything for this computation. So when do you think you should recursively call? Like before you print out or after you cout? Okay, so let's make this very simple. So you come here, this is you right now. You're just like standing here. Here's a pointer. This is you. You're looking at this guy. Do you want to print the value here now, or do you want to go like, hey, I need to go walk down to this guy and then walk down to this guy and then, okay, before, yeah, exactly, before is the right one. You kind of want to be like, hey, I know that this is you here, you're looking at this one node, because the computer would be looking at one node at a time. The parameter is only one node. You'd want to be like, all right, cool, thank you, but I need to go to the next one. I see you, but I know that there's another one, so I need to go to the next one. And then here is when you print out. That's why it's before, because you want to do reverse order, right? So when you are at this node, you just say like node next. And this is how you travel. You started off with here, you're like, hey, I don't want to do anything now. Let me go to the next one. Let me go to the next one. Let me go here. Oh, wait, I'm at a null. So this is going to go back. You go here. And now line 33 is done executing, right? So it says node is not equal to null pointer. No, it is not. So print the value. And so let me draw that. So here is a first instance of reverse. And you give it this node. So this guy has a number 3 inside of it. Line 33, it creates another instance of it. But this time you gave it nodes next. You gave it the address of the next guy. But now this one is holding 4. Again, this one is at line 33, and it's like, create another instance. We got another call. 5. So now again, 5, it's a brand new instance. It's again looking at number 33, being like, okay, create another instance. And then this time, what is 5's next? It's a null. So it comes here with 5's next. It comes here, and it gives it. Now you have another instance, right? So now the problem is that now you're gonna say go to nodes next, which now for your local variable node, the value is null. So what you're saying is that go to nodes next, which this is going to be a huge memory issue. So what's a smarter thing to do? Let's play around with putting this inside of this if node is not null. Because in this case, then it would come here. Now you have at this instance here, this is the top of the stack. This is the first thing that the CPU is looking at. It's going to say, is node not equal to null pointer? It is equal to null pointer. So this whole if block is not going to work, and nothing's going to happen. So this just gets destroyed. And then we go back to number 5, to the instance of the function that has a node with value 5. It's a mouthful. But basically here in node 5, it's kind of like, okay, I did line 34, and the result of it was just a function, an instance that it just died. It is a void, so it didn't return nothing. It didn't tell you nothing. So now that I did line 34, print out the value that I want. So here we get a 5. And for this instance, we got to the end of this if block. After this if block, there's nothing. We get to the end, to the closing braces. So then this dies as well. You're at the instance of the function, which has a node with a value 4. It did number 34. The result of that was just a printout, because this is a void function. It doesn't return anything. It moves on to line 36, print out 4. And then this dies. This gets removed from your memory. And then you get to 3. 3 was waiting on line 34. The result of that was just a printout. The function is a void. It doesn't return anything. Jumps to goes to line 36, which you get a 3. And then this one dies. And then now this whole thing, now this original call to the function now is back to this, because even this one is done. And all you get on your console is the reverse order of your linked list. So the next question is, so write a recursive algorithm that counts the number of nodes in a linked list. So for this one, you would have an existing list that looks like this, and then your output would be just 3. And what I was going to say is that the exact type of explanation that I gave, you need to practice how to solve lead code problems exactly like this, and you need to do this thing in interviews as well. This is a skill that you develop after this semester, once you start interviewing. Okay. So void counting, we got current position, got it in trial. So we have an int count is equal to 0, and if current position is not equal to null, increase count, and then call itself once again, and then print count. Okay. Did you run this code at all? No. Okay. This one, you got another int counter is equal to 0 if node is equal to null is not equal to null pointer. Okay, so yours is the returning an integer, but Karina, it has a void. Okay, I really like it. I mean, respect to both of you, first of all. Let me look at what is happening with Karina's first, because to be honest with you, I do not remember all the solutions. I kind of like come up with things on the fly. That's another perk of constantly on interviewing, but I have an internship now, so thank God I don't have to do this unless for an SI session. I'm going to make this a little bit bigger. So what we have is the count. So I give you the head of this list. So what I would see is count, first of all, is equal to 0 in this instance. Then okay, and then the node that I have is this guy. Looks like that. So if current position is not equal to null, this is not a null. So put count to increases by 1. Okay, so instead of a 0, it becomes a 1. And then create another instance of myself, which is this. It's a new function, so everything gets set up once again. This goes into a 0 because That's what your line 3 is. So it goes, so this one is waiting on line 6, but this one is back up at line 3. And what did you give it? You give it the node that contains the value 2. Cool. So it comes here and it says current, this node, which is pointed to by current position pointer, is not null. So put count up by 1 and then create another instance of this. Count is equal to, and I hope you see what I'm getting at here, right? Like every time you're resetting count. So count is equal to 0. What value did you give it for this? It's a null. So it comes here. This if a statement would not execute for this because you gave it a null. Nothing would happen here. This one would die off. Cool. But then for this one, which was waiting on number 6, yes, yeah. So you see what I mean. So for this one that was waiting on line 6, now this is done, right? So it's gonna see out count, which in this case right now we see it's number 1. So I get a 1 here. And then it's the end of this if block. It's the end of your function. Good to go. So this one dies. And for this instance, it was again stuck at line 6, goes up to line 7, prints out a 1 for me, and then it's done. So you guys really need to think of them as separate instances of the same thing, but they're similar, but they're different. Again, I had to pull up this picture up on you, but like these dolls are the same, but they're different. It's like they're literally the same. Like maybe because of like spacing, they have different sizes, but they're the same, yet different instances. For yours, it's got its own unique set of issues. But yeah, so how can we fix this counter thing? What is one thing that we could do?
Pass it into the function as reference.
Yeah, that would be a pretty good idea to me.